ALIGN-CCUS stands for Accelerating Low Carbon Industrial Growth through CCUS. ALIGN-CCUS is a project within ACT. ACT means Accelerating CCUS Technologies. All 8 current ACT projects are funded by the participating countries and by the EU through Horizon 2020. The countries that are involved in ALIGN-CCUS are Romania, Germany, United Kingdom, Norway, and the Netherlands. ALIGN-CCUS is a project addressing the full CCUS chain. That means that there is work defined on capture, transport, storage, and utilization. The technical results of the project will be used in studies on making blueprints how to decarbonize industrial areas. Also, studies on public perception are an important part of ALIGN-CCUS. Last November, we had a similar webinar like this, introducing the work that is performed in ALIGN-CCUS. This webinar has also been recorded, so you can watch it online through our website. Also, other information about the project can be found there, and you can subscribe to the ALIGN-CCUS newsletter that will be sent out regularly, addressing interesting topics of the project. This webinar is focused on the CO2 utilization work in ALIGN-CCUS. Next. Today we have the following speakers. Peter Moser, who will speak about the introduction to the case for CCU. Mohammed Majid, who will talk about the development of the CCU demonstrator. Herman Josef Laumann, who will speak about the engine adaptation needed for engines to work with CCU-derived fuels. And Stephanie Troy, who will speak about the integration and scale-up of CCU technologies. You can find the biographies of our speakers on our website under the Events tab. I would now like to introduce Peter Moser as the first presenter. Peter Moser is leading the R&D department emission reduction technologies of RWE Power in Essen, Germany. And he's a work package leader of the utilization work in ALIGN-CCUS. Go ahead, Peter.
Yes, hello, thank you, Peter. And my name is Peter Moser. I'm head of the Department Emission Reduction Technologies of RWE Power and in the Research and Development Department. And I'm leading Work Package 4. And I will give you an introduction into this part of the ALIGN-CCUS project. Within Work Package 4 of the ALIGN-CCUS project, a full carbon capture and usage chain will be demonstrated as an element for large-scale energy storage by CO2 conversion into fuels and as a blueprint for sector coupling. So let me start this introduction to the work package with an explanation why CCU can become a very important tool for climate protection. The list of the current goals set by politics and society for the future energy and raw material supply is long and comprises, among others, especially the implementation of the Paris Agreement and the climate protection goals, but also high shares of renewable energy in the electricity production, and at the same time safe, highly flexible and cost-effective energy supply. However, the gaps between the formulated desired goals and the technical reality are increasingly diverging. This diagram here shows an example, the German energy-related CO2 emissions from 1990 until 2015. So, according to the climate protection goals, a reduction of the CO2 emissions by 80 up to 95% by 2050 compared to 1990 must be achieved. You can see here clearly, as an example, this arrow shows a 90% reduction of the CO2 emissions in the diagram to illustrate the challenges. Even a complete withdrawal from the use of lignite, hard coal, and natural gas extended across all energy-related sectors and applications in Germany within the next 32 years is insufficient to reach the CO2 reduction targets. In addition, a large part of the CO2 emissions caused by the use of oil would have to be avoided. As we have no acceptance of carbon capture and storage, CCS, in some European countries, today it seems to be impossible following a sustainable approach to achieve the climate protection targets without CCU. Next. Even if fossil-fired conventional power plants would be not any longer needed to secure the energy system one day in the future, cement and steel production and chemistry and also waste incineration plants will continue to emit CO2 independent of the electricity sector. Therefore, we can learn from this diagram that all economic sectors have to contribute. Power generation, transport, industry and households to meet the climate protection targets. It's very important to understand that the source of the emitted CO2 is irrelevant for the climate protection and also for CCU, as long as in the end less CO2 is emitted and fossil fuels are substituted. So there's no good or bad CO2 emitted. CCU is not a heal-all measure for climate protection, but it can provide fuels and raw material that's made out of CO2 for the production of base chemicals with cross-sectoral use and a wide range of applications. Additionally, CCU products can be considered as chemical long-term energy storage. So the CCU product becomes more green, the more renewable energy is used in the overall process. But in general, renewable energy is limited in their temporal availability. And with an increasing share of renewable power from wind and photovoltaics, their fluctuating nature demands reliable, efficient energy storage systems and backup power. Again, an example from Germany explains this. In January last year, we had the situation that within some days, the power generation from wind and solar changed from more than 35 gigawatts to 0.3 gigawatts. Although the implementation of huge capacities of wind and PV power was very successful in Germany, we can learn from this example two essentials. On one hand, we need for decades conventional power plants to secure the electricity, the power system. And on the other hand, we will need more and more large-scale energy storage capacity. The small rectangular field in the diagram represents the total energy content of the pumped hydro storages in Germany, normally sufficient for some hours. No one wants energy storage as it is connected with cost and efficiency losses, but in the future energy systems, we will need orders of magnitudes higher storage capacities. Energy storage is a prerequisite for a sustainable energy system based on fluctuating renewable energies. And in such a future system with intelligent balancing of the power supply and consumption, CCU can support the security and the performance of the energy supply system. And also it supports the transition of the system itself by a transsectoral approach. Next. Therefore, 8 partners will jointly demonstrate in ALIGN-CCUS a full CCU use chain and also the utilization of a CCU product in the power and transport sector. We follow a holistic approach that comprises not alone the demonstration and optimization of the technology, but also the investigation of the additional benefits of the CCU chain as grid stability and also the socio-economic and environmental value. In ALIGN-CCUS, the captured CO2 from the flue gas of RWE Power's lignite-fired power plant at Niederaußen and hydrogen, which is produced from an alkaline water electrolyzer from Assai Kasai, will be the feedstock for the synthesis of methanol and dimethyl ether, DME. Mitsubishi Hitachi Power Systems Europe is responsible for the innovative synthesis unit, and the produced DME will be used as a fuel in a stationary peak power generator. The necessary adaptation of the engine is realized by the University of Aachen and FEV and the associated partner Bosch. DME can also be used as a raw material for the production of other fuels as polyoxymethylene ethers, OME. Therefore, additionally, a passenger car will be modified to run on this OME fuel. This will demonstrate another possible implementation of CCU synthetic fuels. The technology chain demonstrated in the ALIGN-CCUS project has various co-benefits besides the substitution of fossil fuels by producing platform chemicals, methanol, DME, with many applications in different economic sectors. Coupled power generation and production and use of CCU fuels supports the renewable energy by stabilizing the grid, providing long-term energy storage and peak load backup power generation. Additionally, the use of DME OME as fuels lowers emissions in the transport sector, and I have to point out that this means not only CO2, but especially NOx and particulates, soot, and also SOx. The Research Center Jülich and TNO are working together with all partners on options for the techno-economical optimization of the demonstrated CCU technology and on basis of the techno-economical ecological assessment on real-world data from the demonstration plant. Next. Besides the engineering, construction, and operation of the demonstration plant, it is decisive for our work to assess the technical, economic, and ecological impacts of the demonstrated CCU technology. Here, the life cycle analysis and the comparative assessment is the basis for the evaluation and the optimization of the developed technologies and its application in the energy and transport sector. We will investigate integration costs of the CCU chain technology for large-scale units and decentralized smaller facilities. Our goal is to answer questions like what size of the demonstrated CCU chain is commercially most promising and what is the most promising environment for its implementation. Here we have to weight factors like the economy of scale, advantages and disadvantages of centralized, decentralized CCU units, installation at existing industrial sites or in urban areas, and the need and requirements regarding a transport infrastructure for CO2, power, hydrogen, and the CCU product. And last but not least, what are the requirements regarding the flexibility, startup time, full load hours of the CCU chain? And these questions are also directly linked with a very important factor, public acceptance. So I would like to point out that we are working closely together with the other work packages of ALIGN-CCUS on these highly interdisciplinary topics. Not only the technical and economic optimization is our goal, as for example by measures like absorption enhanced catalysts to increase the yield and performance of the CCU synthesis and new catalysts. Also, we are investigating by what approach the developed technology can be integrated into the transforming energy world to achieve the maximum benefit. In the end, our CCU concept should offer an opportunity for coupling of energy and other sectors and to unlock the potential for CCU, especially in countries that decided against CCS. So it's our intention that the proof of feasibility and viability of the demonstrated full CCU chain in Work Package 4 increases public awareness and also acceptance of CCU as a climate protection measure. So this was my overview about the activities of the Work Package 4 partners from industry, universities, and research institutes, and our motivation. So I would like now to hand over to Dr. Mohamed Majid from Mitsubishi Hitachi Power Systems Europe.
Yeah, a very good afternoon, ladies and gentlemen. My name is Mohamed Majid and I'm working for Mitsubishi Hitachi Power Systems Europe. We are situated in Duisburg, Germany, and personally I am working in the Department of Research and Development in this company. Next. Yeah, well, we see here the task overview, what we are going to do, what our task, our company's task is in this ALIGN-CCUS project. We will be working on the synthesis of this unit. That means we need two main adducts. One is CO2, hydrogen, and we are going to use these two adducts, mix them, compress them, and then provide it to the reactor to synthesize it to the DME, dimethyl ether. Well, CO2 will be supplied from CO2 liquefaction and filling plant at RWA power plant in Niederaußen, Germany. Hydrogen will be supplied from a alkaline water electrolyzer, which will be provided by Asai Kasai Europe. They are also situated in Germany. Well, once we have these two ducts, as I said, they will be transported, supplied to the reactor, and after mixing and heating it up, achieving the required pressure, and then from these two ducts we are going to produce synthesized DME. Next. Here we see a task structure, what we are working on. I mean, our part. We are working in 4 blocks. 3 are shown in blue and 1 is shown in red. I will tell you why it is in the red. Let me start from the very left side, utilities preparation. This is one block where we are concentrating on hydrogen preparation, CO2, which will be supplied in liquefied form, but we need it for the synthesis unit. We need it in the gas form. So we are going to convert it from liquid to gas, hydrogen, and then mix them. Then comes the blue middle block, where we have synthesis unit, both gases mixed up, compressed up, and then come to the synthesis unit. I will go in details of these boxes in short. Then third blue box from the right side is storage. So it is another part, how we are going to store this raw product, which is going to be a mixture of DME, methanol, hydrogen, CO, leftover of CO2, and all this. So how we are going to store it at the site, and then from the site it will go to a red box. This is the distillation part. So from this raw product we want to win very high purity of DME, so that we can bring it, the target is to achieve a quality with which you can run, for example, trucks, and you can bring it to the transport sector. Next. Here we see a process diagram. I have explained it in some blocks. We start from the left side and upper side. We see demineralized water is supplied to the electrolyzer, and after all these processes, let me say, we are lucky, hydrogen with a very high purity is available there, and it goes, as you see, hydrogen line goes down. And then now let me go very down on the left hand side. We see the CO2 capture and CO2 compression side. From this block, the CO2, which is still in liquefied form, comes to the next block, which is actually the gas preparation, CO2 preparation unit, where different unit operations will be applied, and then liquid CO2 will be converted to gas CO2, and both these streams mixed up, gas compressor is there, and then transported to the DME synthesis unit, which will provide us DME with methanol, hydrogen, and some impurities. Next. We have to work on a number of engineering lists. Here I show you just one example, which is CO2 conditioning system. CO2, let's start from the very left hand side. CO2 from RWA side is coming in. Next block is CO2 buffer tank. So we need this buffer tank because something can happen in the plant. Maybe some supply line is having some disturbance. So this buffer tank is there to ensure us the proper and permanent supply availability of CO2 for our synthesis unit. From this buffer tank, it will go to a vaporizer, so that we can convert it from liquid to gas, and then gas will be further transported to there will be a heater, so that we can achieve the required temperature, and then further it goes on, and we can supply it to the synthesis part. Next. Okay, some overview about methods. How can we produce synthesized DME? I show you here two methods. On the left hand side, we see two-step method. and on the right hand side we see one-step method. So what is the main difference? Going back to the left hand side, two-step method, we need here again CO2 is there, hydrogen is there, both are mixed up, and then comes to the after all unit processes, compression and all this, it comes to the reactor part. So we see here reactor A, where we have a catalyst A, which is responsible to convert these two adducts, CO2 and hydrogen, into methanol. And from this methanol, there is also a lot of water, but distillation is also going on. So we have methanol, and then this methanol is further supplied to a next reactor, which we call it reactor B, and it has a catalyst B, which is responsible of the conversion of methanol to DME. On the downs, we can see this. This is very well known. Two-step DME synthesis is well-known method, and a number of companies are already working on this. Don't forget, we need here two reactors. Now we come to the right-hand side, which is one-step DME synthesis, and we are going to use this method for this ALIGN-CCUS project. Here again we see two adducts, CO2, hydrogen, but this time the difference is that we need only one reactor, and in this one reactor we have a catalyst which is actually the combination of catalyst A plus catalyst B. So that means having the both properties of this catalyst, and which is responsible to convert CO2 hydrogen directly to DME, and to avoiding this in between step of methanol production. So it's a new process. Novel reactor we are going to use, and only one reactor is needed for this. Next. What do we see here? We see here DME synthesis catalyst system. This is very important part of let me call it, this is the core of the whole synthesis unit. How we are going to achieve the target that we have a really good combination of Cat A plus Cat B, and then we have a good catalyst to synthesize CO2 hydrogen to DME. I will start from left hand side, from the upper box catalyst design. We are going to based on our own knowledge, know-how, we are going to modify the catalyst to adjust it for the ALIGN-CCUS. And then I come to the next box where we are going to test this catalyst in the lab. What we are going to do, what we will be testing there, we want to see catalyst performance at lab condition. We want to identify catalyst key performance indicators. We want to see the kinetic reaction measurements, which will provide us a data for the development of kinetic reaction model. We want to learn how can we avoid or minimize catalyst deactivations. Water, for example, is a big factor which can deactivate catalysts, amongst other poisons, for example, some gases. Well, we want to see here boundary conditions for catalyst poisoning. That means how much this catalyst can bear without this deactivation starts from a specific gas or from a specific element. We want to learn suitable operation conditions. How should we run our synthesis unit? We want to see catalyst tolerance towards impurities, for example, oxygen. Where can oxygen come in? It is possible that oxygen can come in from electrolyzer side. Yeah, there's chances. Ammonia chances, or some other volatile organic compounds, or sulfur components and other critical species. So we have to learn how to avoid this and what are their influence. On the left hand side, third box, which is testing in demo plant. That means once we are satisfied in our testing in the lab, we say, so now it's time to bring this catalyst to the real demonstration plant. We will put it in there. We will see now what happens in the demo plant. And then we compare our results from the lab, and I'm sure once we do it, then we will see there is still some potential for the optimization. Once we learn this, then we will go back and we will optimize the catalyst, and then from the left fourth block, which is catalyst optimization, we will move back to the upper block, which is again catalyst design. That means we will learn optimization steps, we will bring this optimization into the catalyst design, and then the loop will go on, and we will do it at least 2 to 3 times, so to really to get a really good combination, really good catalyst for the synthesis unit. So this is the scheme how we are going to have a really good catalyst system in the hand. Next, please. Okay, here I show you just an example of laboratory setup, which we are going to evaluate our catalyst. Let me say, which we just produce for the synthesis plant. This picture, this setup is going to be a high pressure, high temperature packed bed reactor for our lab scale evaluation of the catalyst. As I said, to achieve all our targets, which I just explained you a couple of seconds ago. Next. Well, let me say we have catalyst, we have reactor there. Our synthesis unit is working perfect, everything is going good. Then we have DME, dimethyl ether, and we have to store it at site. How big these tanks are going to be, this is a factor of product quantity as a result of commissioning test and testing operation. But I can tell here we are working on this, but we know these tanks are going to be pressurized storage tanks. We have to consider here control to the leakage. We have to consider the excess pressure buildup in the tanks. If the temperature goes up, pressure goes up, we have to consider this. We have to consider emissions to the atmosphere. We have to avoid this, and also sump under tank if some leakage somehow happens, we have to do this. On the right hand side, we see just 2 example pictures how these tanks can look like. Okay, well, this was it was all from my side, and then I will give word to my colleague Herman, so he will tell you.
Hello, I have a problem with switching my microphone, my camera on. So thank you for the introduction. My name is Herman Joseph Laumann. I'm working at FEV for more than 30 years, mainly on the field of fuel injection equipment and fuel injection systems, and of course as well on the field of special fuels and their properties for in regard of fuel injection systems. So I come to my presentation. Next slide, please. Here you see, in principle, the whole chain. Once again, we start with the electrical power or water power generating hydrogen on one hand, and CO2 sources we need. And with both hydrogen and CO2, with the chemical synthesis, which has already been shown, we are able to generate synthetic fuels like DME or OME, which can be used as fuels for combustion engines or even also for vehicles. Next slide, please. One example is the DME. Here are the main properties of the DME. The oxygen content of DME is around 34% or 35%. That is very important number, because one benefit is surely that the combustion has a significantly reduced soot emission. The heating value is, of course, due to the high oxygen content, relatively low. It's reduced by the same percentage, around 1/3. But very important issue is also the kinematic viscosity of the liquid, which is really very low. It's 0.1 centistokes related to approximately 3 centistokes for diesel. That means we need to have very special injectors and pumps as well. In the right-hand diagram, you see the pressure, the evaporation pressure versus temperature. At room temperature 25 degrees C, we need a pressure of approximately 5 to 6 bar to keep it in the liquid phase. At the engine, where we have temperatures of 90 degrees C, you see that we have to have 30 bar liquid pressure in order to avoid evaporation of the fuel. Therefore, the injection system has to be capable for a really high feed pressure of 30 bar. Next slide, please. Here you see the benefit of the fuel. At first, you're shown the normal trade-off between NOx emission and soot emission, starting on the right-hand side. That is a very low smoke number on one hand, but a relatively high amount of NOx emissions. If we enlarge the EGR rate, next please. If we enlarge the EGR rate, we are going down with the NOx emissions of the vehicle or of the engine, but on the other hand, the soot emission is growing. Next, please. With the that was for normal diesel fuel. With future fuels like Fischer-Tropsch diesel or red methyl ester like biodiesel, we are able to reduce this NOx particulate trade-off significantly. And the green line shows here in this case that this NOx particulate trade-off is nearly gone. There's only a very small maximum of the smoke emission in the area of 0.3 gram per kilowatt power of NOx emission. Next slide, please. Yeah, due to the special properties of DME, we of course have to have a fuel tank which is similar to that which is known in the field from LPG. We need to have a tank with a pressure of 5 bar to keep the fuel in the DME in the liquid phase. Of course, also the materials has to be adapted to this special fuel. It has to PTFE has to be used, for example, for the fuel tank. Next, please. The low pressure pump I already mentioned has to be able to supply a pressure of 30 bar in order to avoid evaporation at the hot engine environment. This is done by a membrane pump. The membrane, of course, has to be again protected for the DME fuel. So the membrane and the sealings are also here designed from PTFE. This pump has no leakage to the pump drive, so that is surely beneficial for this gaseous liquid. Next slide, please. Then the high pressure pump. Again, here are material problems. We have to use also here the sealings in PTFE. Of course, at the plunger shaft, there also must be a sealing. Normally, the diesel pumps are not sealed. The plunger barrel assembly is that tidy that the diesel loss is really very low without any sealing. But here in this case, where we have fuel which is gaseous at ambient temperature, we would have the situation that we are going to press a significant amount of gaseous fuel into the lubrication oil of the pump. And we of course need an oil lubricated pump due to the fact that the viscosity of the DME is a factor of 30 lower compared to diesel. So a fuel lubricated pump cannot be used in this application. We need an oil lubricated pump and also a special sealing at the plunger in order to avoid mixing the fuel into the oil. Next slide, please. At the injector side, we are going to use a truck injector with the highest possible nozzle flow rate, which is around 1300 cc per 30 seconds at 100 bar. The injector does not have any static leakage. There is only the servo leakage which have to be feed back to the low pressure system. To the next slide, please. Yes, that is the next fuel which we are also using. The DME will be used for industrial engine, and the OME will be used in a passenger car. The OME has the advantage that the OME is in a liquid phase. We are working here especially on the OME 3 to 5. That means there are longer chains, so that the evaporation temperature is similar to that what we know from the diesel side. The sealings for in the injection systems again have to be designed from PTFE in order to be resistant against this fuel. And due to the high oxygen content, of course, the heating value is again reduced, so that we need to inject a much larger injection volume or injection quantity compared to diesel. The next slide, please. This slide is showing a high pressure chamber where we are going to make spray investigations. The chamber has a continuous airflow of about 50 cubic meters per hour, and it allows static boundary conditions with a maximum pressure of 140 bar and a maximum temperature of 1000 Kelvin. The optical chamber has 3 circular windows with a diameter of 120 millimeters for spray investigations. On the right hand side you see the arrangement. The air entry is at the bottom, and there are heating cartridges for heating up this the air, and the investigated spray is injected by the injector at the right hand side, and through the windows we can investigate the fuel spray and make camera films which are shown in the next slide. Next, please. Here you see one example. The nozzle is on the left-hand side, injecting at first a liquid phase. The liquid phase has a certain liquid penetration, named here with the abbreviation LPL, and during injection also the evaporation takes place, and the evaporated fuel then allows the start of combustion. You see then colored the flame, and there is the lift off length LOL defined in this slide. That is the distance between the nozzle and the begin of the first light emission, and the gaseous penetration length is then the on the left hand side, on the right hand side, sorry, the end of the flame on the other side. Yes, next slide, please. That is a movie showing the difference we see in diesel and OME1. OME1, one remark to OME1, that is a liquid which is evaporating at about 40 degrees Celsius, and the cetane number is really poor, and that is the reason why the OME1 starts burning relatively late. You see here the diesel burns around 35 millimeter after the downstream the nozzle, and the OME starts burning at around 80 millimeter downstream the nozzle. That will surely change in case that we use OME 325. In this case, the cetane number is much better. Coming to the next slide. Here we see a simulation, what happens in the combustion chamber. You see half of the piston bowl, and the colored area is the combustion chamber. Blue means it is a relatively lean mixture. Red is a relatively high mixture, and green means that the mixture is at the end of the expansion stroke around 1.5 as for the air fuel ratio. Yeah, you can see here quite nice during injection. It is relatively a rich mixture, a red colored mixture, and this is then relatively fast gone into the green color, which is the air fuel ratio, which is very good for the combustion. To the next slide. Yes, here is the engine shown. That is a truck engine which we are going to operate with DME. Of course, the high pressure common rail pump needs to be adapted for the special fuel for the DME, and of course also, as I mentioned, the injector will be modified in order to reduce or to eliminate static leakages. Of course, there will be a servo loss, which has to be feedback to the tank anyway. Yes, and this engine will then be going to be operated at RWE factory sites in Niederaußen. Next slide. So that's from my side so far, and I want to hand over to Stephanie Treu from FZ Jülich. Thank you.
Yes, thank you for this. Good afternoon. My name is Stephanie Treu. I work at a research center in the Forschungszentrum Jülich, situated in the west of Germany. And my task in ALIGN is conducting a life cycle assessment of the demonstrator you have just heard a lot about. Next slide, please. So I want to start off this presentation by talking about definition of life cycle assessment. What is it that we do and why do we do it? In our life cycle approach here in this project, we will work as a cradle to grave approach, and that means that we consider all material and energy flows throughout the life cycle of a product, and we determine the environmental impact. And when I talk about life cycle, I mean their construction, operation, and disposal. Classically, we work on a life cycle assessment in 4 steps. The first one is the golden scope definition. So here we determine where our system boundaries lay and which parts or what exactly we want to look at and where we draw our limits or our system boundaries. The next step is the life cycle inventory, and here we collect lots and lots of data regarding our product and also model our system. In the next step, the impact assessment, we basically translate this data that we have collected into environmental effects and calculate emissions. And lastly, in the interpretation, we draw conclusions from these results. And in general, these steps are iterative, so we might jump between the different work steps throughout the process. Next slide. So what will be our aim for ALIGN? We want to investigate the complete process chain, and we want to calculate environmental impacts for a broad area of impact categories, such as you can see in this table here. And we want to depict environmental impacts for the usage of DME and for OME as a synthetic fuel in the transportation sector, and also for peak power production. We want to analyze a wide area of scenarios of this concept and potentially competing technologies. And we hope that by doing this, we will be able to classify our results well. And our results can support developers and give valuable feedback regarding potential environmental benefits and also pitfalls. Next slide, please. Here you can see the demonstrator you have already heard a lot about, and we want to look separately at all the different parts, and then of course also have like a result, a summed up result at the end. So the first little parcel we want to look at is a power plant with its CO2 post-combustion capture. We will also look in detail at the hydrogen production via electrolyzer, then also the DME and OME synthesis unit, and the use of DME and OME for peak power production and also for transport. And of course, also very important is looking at competing setups, so we have something we can compare our results to. Now, what sets us apart from other LCA investigations on CCU with DME is that we want to set our system boundary a little wider and not only investigate up until the production of the DME, but as I just said, also its usage. And therefore, our competing cases or our reference cases will look a little different to the ones in the literature. And determining what these reference cases look like, that has been my target for the past months, and I would like to show you the status of my work for the mobility reference case. Next slide. So here you see the mobility reference case that I set up, and it's a 2-path system. You can see on the top the electricity generation. We have our power plant, and the power plant generates electricity and also has certain emissions. And then in the other path, we have diesel production with a certain amount of emissions, and that diesel powers then a car that can drive a certain distance and also has emissions. Next slide. If you now add numbers to this, then you can see that for our 1 kilowatt hour of electricity that the power plant generates, we have emissions of 675 grams of CO2 equivalents. And on a mobility path, the diesel production leads to 57 grams of CO2 equivalent emissions, and our car can drive 4.16 kilometers and emits 569 grams of CO2. You might be wondering where 4.16 kilometers comes from. It's a bit of an odd number. Bear with me, that will become clear in just a minute. But first, next slide, please. First, I want to show you how we now get from our reference case to mobility with OME. And to do that, first we need to lose our diesel production. We don't need diesel in our OME case, and all the emissions that go with this diesel production also don't occur. Next slide. And instead we add PCC, a post-combustion capture, to our power plant. Then the captured CO2 is being used for OME production together with hydrogen from an electrolyzer, and the produced OME then drives our car. Next slide, please. Now, if you add figures to this one, you can see that the unit power plant together with post-combustion capture only emits 50 grams of CO2 equivalents now, so a very large reduction here. We capture 765 grams of CO2, and together with a good 100 grams of hydrogen, we can produce 392 grams of OME. And these 392 grams can drive our car for 4.16 kilometers. So this is where this odd number comes from. We also have emissions from the car of about 765 grams CO2. Next slide. Now that's a lot of numbers. I tried to sum this up on a summary sheet. So we have a functional unit that's 1 kilowatt hour electricity. And when producing that, we can capture 765 grams of CO2. That in turn then produces 392 grams of OME that can drive our car for 4.16 kilometers and replace 177 grams of diesel. If you think back now to our two-path system, that the one without OME, then the total CO2 equivalent emissions for this systems were 1.3 kilograms of CO2 equivalents. For our OME mobility case, if we add all the known emissions here, we are at 0.8 kilograms, which leaves us with a margin of about 0.5 kilogram. But we haven't included all different aspects of the LCA yet, because no, that is the task of this project, obviously, and we don't have the data yet. What is not included? So basically, construction and recycling for all components is not included. So no, not for the power plant or the post-combustion capture, not for the OME, DME production facilities, the electrolyzer, neither the car. They can all impact both cases, or well, some of them can impact both cases, some just one of the above cases. I think they will probably not impact them largely. What will have a big impact though, and that is not considered yet, is the operation of the OME production and conditioning facilities, and also of the electrolyzer. Those will be energy intensive processes, which usually means they have a quite high impact. How high this impact will be also highly depends on where the electricity for these steps come from. So this will be a very interesting aspect to look at in the near future. I should also add that for the OME mobility, so far I could only estimate the emissions, and it will be very interesting to see what the actual emissions look like at the end of the project, once our partners have done some measurements and some experiments. Next slide. So what will be my next steps? What you have now seen for the mobility case, we also want to do for peak power, for the peak power concept. And here I will need to find adequate competing technologies to be able to compare our results well. And I will also look at DME OME synthesis processes very soon. I will estimate construction and recycling efforts, especially for power plant and post-combustion capture for now. I can do that based on previous works that we have done here at the Forschungszentrum Jülich. And I've just received data on the electrolyzer, so working on the LCA here will also be one of my next steps. And everything you have seen now here is for the category of global warming potential, so CO2 equivalents. As I said, we want to look at a long list of different impact categories. So looking at those is also one of my next steps. And with that, I thank you now, and I will hand over the word for Peter van Os for the Q&A now. Thank you.
Yes, well, thank you, Stephanie, for your presentation. Also, I want to thank all the other presenters for their presentation. We're now going to begin to answer the questions that were submitted during today's presentations. And as a reminder, you can still submit questions to the questions panel on your screen. And our first question is actually to Peter Moser. Let me check if I have it here. So, Peter, do you have an idea of the overall efficiency from the energy efficiency from the chain from CO2 and renewable electricity to transport use and regeneration?
For sure, we have an idea, but it's to say it frankly, up to now, from my point of view, it's too early to answer this question. There are some ideas we have how we can optimize the overall efficiency. For sure, CCU is connected with a loss of efficiency. But as I've tried to explain in my presentation, this is true for all energy storage technologies. And we have carefully to look in the end on the results of Stephanie on what says the life cycle analysis. So you know, we have to compare and to compete with other technologies, and this, the efficiency, it's also the costs, but it's also the how can we really implement the technology in our system. So it's not so easy only to say the loss of efficiency. But we have first figures, but it's too early to communicate them.
Okay, thank you, Peter. So we will learn more about that in the future of ALIGN-CCUS. The next question, I guess, is for Herman. What is the advantage of using DME as transport fuel compared to using the hydrogen directly in a fuel cell vehicle? Can you say something about that? Herman, are you there? I can't hear you, so your mic is still switched off.
Yeah, my microphone was switched off. Hydrogen is surely not that easy because it has to be handled either in a high pressure vessel, that means much more than 5 bar, or it has to be stored in a cryogenic way. And DME is surely much easier to handle. We can more or less use that what is known already from LPG as fuel for vehicles.
Okay. Thank you for that clear answer. I think the next question is for Stephanie. You mentioned you have looked at also previous LCA studies, and how does your LCA study in ALIGN compares to the LCA studies that already have been done? Is it more extended or more practical, or are you using more data from the demonstration? Can you say something about that?
I assume you mean compared to work from literature that we have found in the area, or did you mean previous works that we ourselves have done?
No, more work. Yeah.
Sorry?
More work from literature.
Literature. Yeah. So what we have found so far in literature, the investigations looked at CCU up until DME, the DME production, and not the actual use of the fuel that you have. So if you then compare your results, you compare it to other well, to how you usually produce your DME, which is not what we really want to do. We want to use the DME, and we don't want to replace DME production up until today. We want to replace diesel in a car, or we want to replace other peak power methods, production methods. So yeah, we definitely want to go that step. We want to look at what is the result after we have used our DME or our OME, and that will make our results a little difficult to compare, I guess, because the results be very specific, but I hope it will give a very clear picture of where we are where we fit in and how we fit in with these competing technologies.
Right. Okay. Thank you. The next one is from Mohammed. Actually, there are two questions in one. What will be the footprint of the installation you are putting up at the RWE sites? That's one question. Another question related to that: are there any special precautions because you are using hydrogen on the power plant site?
Okay, first question I couldn't understand, but second question, precaution. Of course, we have to deal with hydrogen, and we have to see all what can happen, what kind of tanks and what kind of compressors, heat exchangers are used in this electrolyzer. But let me say, the hydrogen will be produced in an alkaline electrolyzer, and the company Asahi Kasei, they have a lot of knowledge about handling this hydrogen. So we are working together with our partners, and we are going to cope these handling issues. And I'm sure we will do it in a very, very safe way together. Can you repeat first question again, please?
Yeah, that was referring to the footprint. So how big will the installation be? How many square meters and how high?
Installation. Okay. Maybe Dr. Moser can also help me in this way. We are planning they will to put this instrument, the whole plant, in form of containers. For example, there will be one container which will be around 20 foot for electrolyzer. Then we will be having a container for synthesis unit, which will be around we plan for 40 feet. So you can see the dimensions almost how big this installation is going to be. We have two containers, one for hydrogen, one for synthesis plant. Then we have carbon capture and preparation unit, which is also not like we know real chemical plants, because one thing is very important. What is our target to what is our production target from this ALIGN-CCUS? And let me say this is 2 kilograms per hour of DME mixture. That means in the whole day we are producing 50 kilogram of this material, of this mixture. So in this way we can we can have the idea how big this installation is going to be. As I explained to you, I just summarize it. We are going to work in form of containers, 2 or 3 containers put on the LVA site, and all this equipment made with a how to say protection grid, so that no one can enter. And this is almost the you can get the dimension how big this installation is going to be.
So if I might add, so to both questions regarding the use of hydrogen, so it's nothing new in the end at power plants, because we use hydrogen for the cooling of the turbine, or the generator, better said, of the 1000 megawatt unit. So there is also a big tank of hydrogen existing on the site. And regarding the size, you can also then add, or you have to add then also the CO2 infrastructure. So we have our CO2 post-combustion capture pilot plant that is also part of work package 1 of ALIGN-CCUS. And then the CO2 infrastructure. So we have a compression and liquefaction unit, and a storage tank with a capacity of approximately 20 tons of CO2. and this will feed then this special preparation, CO2 preparation and treatment unit of Mitsubishi.
Okay, well, thank you, Peter and Mohammed, for this answer. I guess the next question is also for Peter Moser. It says that there are recent studies that the assumptions that we have a lot of surplus on renewable energy in the future, that is being challenged more and more. And given the high capital investments of CCU plants and electrolyzers, how does this influence the recovery of the capital and the price of the CCU product? Can you say something about that?
Yes, it is really a good question and a let's say hot topic. For sure, we also don't believe in large amounts of excess power for the next decades. Nevertheless, if we see that the renewables, photovoltaic and wind, will be installed as it is planned, we will see more and more situations where we have a high amount of renewable power in the grid. But it might be that this is not, but up to now I know this is a leading argument often, but I think we should more focus on the periods where we have not sufficient power, because this is much more critical. Excess power, regarding the business case, it is thought, we have electricity for free, or we will earn money because by using this electricity. But in this situation, in principle, power is waste. So much more interesting is the periods when we have calm wind conditions for 10 days or 2 weeks or so. This, in German, it is called also Dunkelflaute. So there's almost less than 10% of the installed capacity is producing from the renewables. And these are the situations in the future that are much more interesting. But it is also, I try to make it understand that this is a topic we will investigate. So what is the philosophy, how we should operate it? How flexible should a CCU system be in the future? So will it follow more the electricity grid to stabilize it, in the sense that it uses on a short-term excess power, and will, or is it more continuously operated and will store electricity for the phases where we have almost no generation from the renewables? Because then we will need huge amounts of energy, this is I think a very important topic for our work, and this has impact of everything: the cost and the business case and the timeline, how we can implement this, because it will also have an impact. Will we come to bigger units or more decentralized? So this is really a very complicated question, but we will try to answer it.
Yeah. Okay. Thank you, Peter. There's also another question from that is engine related, so I will pose that to Herman. Can also every existing car be easily adapted to use the CCU derived fuels, or are there very costly modifications needed?
Yes, as I already mentioned, the ceilings are surely different to these which we know today. So for existing cars, it is surely a much bigger step. That is surely a way which needs to have also some development on the injection system area.
Yeah. Okay. So modifications are needed also in existing cars, but it's possible to do. That's more or less.
It's not impossible, of course, but as I already mentioned, the heat value is much lower. That means we have to inject a higher fuel volume, fuel quantity. That means also that the power output related to diesel is maybe a little bit lower. I don't want to guarantee that the engine will be able to deliver the power which is known from the diesel operation.
Right. Okay. Thank you. This question is referring to a slide from Stephanie, but so I'll also to her, but I don't know if she's the right person to answer it. But in your slide on mobility with OME, you also showed an electrolyzer which has a CO2 that produces CO2. Can you explain that, how that is possible?
Yes, that was meant not as an actual like exhaust or emission from the actual electrolyzer, but more from the overall process of the electrolyzer. So the electrolyzer will need electricity. That electricity will, well, we don't know yet where that will come from. It can come from renewable energies or from the grid, basically. But with electricity always comes a certain amount of emission. So from the production phases of the wind energy converter, for example, or also from the coal input into the power plant, depending on where that electricity comes from. So that emission at electrolyzer is just I guess a placeholder for all emissions that are generated throughout the whole life cycle of this electrolyzer and of this, I guess, kilogram of hydrogen that it produces.
Okay, thank you. There's also questions why from the audience that requested why DME and OME are discussed. It said, it seems to me, I think that's one for Peter Moser, I guess. It seems to me that the losses to go from DME and OME are rather small, and the advantages for the vehicle and on the engine. And let me see what it says there. Yeah, I'm not really understanding the question, so let me read it for a while. Yeah. I think the background from the question is that I'll just read it out loud, but I don't understand the question very well. It seems to me that the losses to go from DME and OME are rather small, and the advantages for the vehicle, no pressurized tank needed, and on the engine, less problems expected with lubricity. What is the reason to pursue DME? I don't really understand the question rather very well, but Peter, can you say something about it? Or
it's funny, when we planned this project, we discussed what is our target molecule, and we came very, very fast to DME. So the reason is, I think there was a question regarding efficiency of the chain. So we should have, for a good efficiency, a small molecule. Then there's a question, for example, in connection with the transport sector, what fields of applications we see for DME, and what are the competitive technologies? So, and for sure, yeah, the competitive technology are electric driven cars, but you all know the disadvantages also of battery cars. So they have a high CO2 footprint before they have been driven 1 kilometer because of the production of the batteries, and the capacity of the energy density is very bad in comparison with chemical storage, and yeah, there might be a mix in the future. I mentioned that the CCU is not a heal-all technology. It is not the only measure for climate protection. So apply CCU, everything is fine. No, that would not be true. But it's the same for batteries. So, and we have to compare where can we use the different technologies. So, and DME has a potential in long distance transport for trucks that has and heavy duty trucks. So, and this is the field where also the batteries will have challenges for the next decade. So now keep in mind the timeline for CCU. What I've shown, we have not many years to come to a significant reduction of the emissions. So and there we need this sector coupling, and DME is a very good candidate to produce out of these chemicals. Keep also in mind that it in principle is a product of methanol. So you can form chemical compounds for the chemical industry, for as a startup or starting point for transport, but it is also a high dense energy storage system, and we will need this. When I've shown in my slides is the pumped hydro capacity in Germany, it's 42 gigawatts. Yeah, we will need a factor 10 or 100 more if we come to 80–90% renewable system. I don't believe that we can do all this with lithium-ion batteries. We will need chemical storage, and DME is a very good candidate. It is regarding the treatment or the handling of the stuff. It's a little bit like LPG. So there is also some infrastructure at filling stations existing up to now. So these are all arguments for DME.
Okay, and what does
and one other hint from my side. I mentioned already during my presentation that DME has the advantage that the particulate emission is rather low. Maybe that also the diesel particulate filter can be reduced in size or even avoided.
Okay, and what is then the difference between using DME or OME? Herman, can you maybe say something about that?
Yeah, the difference is that OME has the possibility that it can be handled as a liquid fuel. It has an evaporation characteristic, which is closer to that what we know from diesel. And the DME has to be handled as already mentioned, as LPG. So it has to be stored in a gas tank under a certain pressure. In order to keep it in the liquid phase. Of course, as I mentioned, also the pre-pressure system has to be laid out in a different way, because we have to make sure that also at the hot engine environment the liquid or the fuel is still in a liquid phase. That means 30 bar at 90 degrees Celsius. And so far, for the DME, there is, of course, a certain effort required to keep it in the liquid phase. And that is not the case if we would use DME, OME 3 to 5. That means a little bit longer change. Again, they are oxygenated fuels. That means particulate emissions are significantly reduced. But in this case, the generation or the synthesis of OME is surely a little bit more complicated related to DME.
Okay, so if I understand well, then OME might be easier to use in a car, but it's more difficult to produce.
Yeah.
Than DME. That's more or less your answer.
Yeah.
Yeah.
Right.
Okay. Then I understand. Thank you. I think the next question might be from Mohammed. Current DME production from methanol also emits CO2 as a process stream. Is that difficult for the technology you are developing in ALIGN, or is it more or less the same? I think your mic is still off, Mohammed.
Thank you. There are two different methods. I had also one slide during my presentation. this well-known technology, which is actually this two-step method, let me call it. I also explained that we need there two different catalysts. We need also two different reactors. So this technology is well-known and state-of-the-art technology. A lot of companies have a lot of success in this part. But if we come to the other side, which we are trying here in ALIGN-CCUS, which is also innovation in this project, that we are trying something different. So it is a different technology. It is also not so easy. It is also there's not a lot of knowledge existing in this part. If we try it in one step, that means we need a very good combination, which is a combination of catalyst, which is producing methanol, and at the same time dehydrating it to DME. Yes, this is not very easy, and also it is different from the one-step well-known technology. Yes, this is different.
Okay, thank you. And there might be another question related to this. Can this technology also be applied for industrial sites, or for process industry or cement industry, or is it really related to post-combustion capture from power plants?
Sure. If we see, we need, what do we need for this? We need hydrogen. Mostly, it will be mostly electrolyzers will be source of hydrogen. Now comes the question. If I understand question right, the question is, what is the source of CO2? Well, we need carbon dioxide for this process. And now, if it comes from power plant, if it comes from cement industry or some other industries, the deciding factor will be what is the quality of this CO2 which is coming in. So we have to see which quality is coming in and how we have to deal with this quality. I give you one example. If there are some sulfates in this carbon dioxide, or coming with the carbon dioxide stream, then we have problem with the catalyst, because catalyst is very conscious, very let me call very sensitive to some impurities, and it has some kind of let me call tolerance for some other impurities. So now this is the deciding factor. What is the source? It can be cement industry, it can be some other chemical plant, but we have to see which quality is coming in, and then we have to let me call to treat it, or we have to bring it up to a level where we can bring it to the reactor where the catalyst is actually implemented. So the very important is that it does not deactivate catalyst. That is so. Of course, I summarize. Yes, there could be different sources of CO2, but the quality of CO2 has to be predefined so that it can go to the synthesis phase.
Okay, thank you. That's clear to me. I have another question related to the life cycle assessment. So for Stephanie, it says here, well, in your LCA study, you're looking at the saving of CO2 emissions when you are using CO2 from a lignite-fired power plant. But are you also looking in your LCA study if, for instance, we are using a far more decarbonized grid, so without or with far less coal in the grid? Then you have at least for the grid also less emissions. And do you also look at that in your study?
So basically, if we look into the future, I assume the question means when the grid mix changes, when we have more renewable energy in the grid. Yes. So well, our CO2 source can change. That wouldn't necessarily impact the assessment all that much. We will still have CO2 sources. What will change is the electricity that all our different processes use. So especially, I guess, for the electrolyzer and the DME, OME production facilities, or well, basically for every step that that uses electricity, that will that will benefit from a different mix, or a mix that has a higher content of renewable energies. And well, in short, the answer is yes. We will look at different mixes at different percentages of renewable in the mix to see. I assume there will be like a break-even point or something like that in the future. So at what point or how much renewable needs to be in the mix to tip the results into well, into our favor, I guess, to make DME the better solution compared to using, for example, diesel in the car. So yes, we want to look at different electricity mixes.
Okay, thank you. So that's good news. I think that there are still quite some questions coming in from the comparisons between DME and OME. So people are asking themselves, yeah, if you make DME, which is more easy to make than OME, but OME fits better into the car engine. What are the pros and cons, and what is the preference from the presenters? And I think I will ask these questions with a short answer, because we're running out of time, to Peter, Mohammed, as well as to Herman. So Peter, if you will go first.
You should also ask Stephanie, because the life cycle analysis is decisive.
Yeah,
but
all four people maybe.
So short answer, from the perspective of a power plant operator that have to provide in the future peak power, it is easy to handle DME as a fuel. So DME is preferred in the energy sector. Okay,
and Stephanie, will you go next?
Yeah, from the figures I know so far, the OME and DME production processes use a similar amount of energy, but have different output levels. And from an LCA point of view, currently DME looks a bit better, but it very much depends also on how it will perform at the end, so at the peak power motor or the car. I don't have any data on that yet, so it's still, you know, I'm not sure yet. I can't say anything definite yet.
Okay, Mohammed, what is your idea?
Yeah, I can tell you something about DME, which I already tried to explain about OME. I am not an expert of OME. I do not have a lot of knowledge about it. But what I know, there are a number of groups, many groups I know, which are already working on OME. There are projects running on about the production. They are sorting out which routes they can take. There are different routes which can bring you to the OME target. My answer is very, let me say, very non-critical. Number of groups are working on OME, and Dr. Moza also explained there will be a mix in the future. So someone should also look at DME. So we are considering this part, and we are looking to fill this gap. What are the chances for DME? Yeah.
Okay, thanks, Mohammed. Short reaction from Herman also, from the engine part, DME or OME?
Yes, I think we should focus on both and learn from both fuels the properties regarding engine emissions, and of course finally the overall efficiency from the production to the wheels. This efficiency chain is important, and the best, of course, will make the race.
Okay, thank you. I think that this will end our questions answer. I have one remark from someone on the question pane that says that Ford prefers DME as well. So let's see how this will end. I would like to thank all the presenters, of course, for their presentation and their answering all the questions that has come in. And I think there were quite some interesting questions. So I want to thank everybody, and I also want to thank all our participants for attending today's webinar. Once you leave this session, you will receive a survey on the presentation, and we would appreciate if you would complete that and provide your feedback, because that will help us in our future webinars. And you will also receive a follow-up email within the next couple of days with a link that you can look back at our webinar. So on behalf of the presenters, the organizers, and I would like to thank you for your joining us today, and have a great day today, and thank you for participating. Okay, bye-bye.
Bye-bye, everybody.
Bye-bye.
Bye.